Today the question is, well, what happens to series that don't have all non-negative terms? Remember that if we had series with non-negative terms, we were able to sometimes use the modified limit comparison test. That is for series with non-negative terms. What if they don't have non-negative terms? Well, sometimes we can apply other results. And we start with the definition. We say that a series is absolutely convergent if the series of absolute values is convergent. Get it? Absolutely convergent, you look at the series of absolute values. If that is convergent, then we say the series is absolutely convergent. Now let's look at a couple of examples. It's easy to note that if our series has non-negative terms to begin with, then absolutely convergent is the same as convergent. Okay, but let's look at some series that don't have all non-negative terms. The first example I want to look at is the summation minus 1 to the n over n running from 1 to infinity. Well, that's got negative terms in it. Anytime n is odd, minus 1 to the n is negative. So I cannot use the modified limit comparison test on this series because this series doesn't have all non-negative terms.
Okay, I found this on the web.
So let's ask, is it absolutely convergent? Because at this point we can't answer the question, is it convergent? Well, to be absolutely convergent, I'd have to look at the series of absolute values. Okay, so if I take the absolute value of this, my minus 1 to the n goes away. And what am I looking at? The summation n running from 1 to infinity of 1 over n. Well, what's that? Remember, that's the harmonic series. It's the p series when p is equal to 1. And what does that series do? The answer is it diverges. So this series, the original one, is what? Not absolutely convergent. Now, is it convergent? The answer is, I don't know. But I know it's not absolutely convergent. And by the way, what's a big thing about absolutely convergent? Well, we have this theorem down here that says, if a series is absolutely convergent, then it is convergent. So in fact, if I determine that a series is absolutely convergent, I know it is automatically convergent. But the first example I looked at, the series is not absolutely convergent, so I can't say that it's convergent. I also can't say that this series is divergent. All I know is that it's not absolutely convergent. All right, let's look at another example. The summation minus 1 to the n over n squared. Well, so if I want to determine whether or not that's absolutely convergent, I look at the summation n running from 1 to infinity of this absolute value. And when I take the absolute value, this minus 1 to the n goes away. Okay, so the series n running from 1 to infinity of 1 over n squared, what does that do? Well, remember that's a p series, 1 over n to the p. What's p? P is 2. P is greater than 1. And when it's greater than 1, the series does what? Converges. So what do I conclude? I conclude that this series is absolutely convergent. But what does my little theorem say? That if a series is absolutely convergent, then it is convergent. So let's apply that here. This series is absolutely convergent. Why? Because the series of absolute values converges. But if it's absolutely convergent, it must be what? Convergent. All right, so let's just repeat what I just said down here. This series, minus 1 to the n over n squared, is what? Absolutely convergent. Therefore, what? It converges. Now, if I were to look at this series, there's it's got a minus 1 to the n. That says some terms in here are positive, some terms are negative. I just cannot use the modified limit comparison test because that's only good for non-negative terms. But I can look at its series of absolute values. And the series of absolute values makes that minus 1 to the n go away, and all these things are positive. Okay, so now let's look at this. Well, I can use the modified limit comparison test on that one. And what am I going to compare it to? Well, what's the highest power of n upstairs? 2. The highest power of n downstairs? 4. So what am I going to compare it to? 1 over n squared. And I'm going to use the modified limit comparison test. And when I do that, I claim that I get a number. When I take the limit of an over bn, I get a number that's not 0, which tells me that this series converges if and only if this series converges, but I know this one does because it's a p series p equal to greater than 1. Therefore, this series converges, which tells me what? This series converges absolutely, but any series that converges absolutely also does what? Converges. So the thing to remember about absolute convergence is it is stronger than converges. So if it's absolutely convergent, it must be convergent. It's not true that if it is convergent, it must be absolutely convergent. And we will see that in the next lecture. Well, I think I've said all I want to say in this video, so bye.